Hello, AP Calculus students. So today looking at a case in Unit 1 from properties of limits, and then also the limit of composite function with a couple side reminders here for you as well. So we're looking at, in particular here, days from the notes. Actually, let me scroll back here and see. Days 3 still, I believe, and then also the idea of day 4 in there as well. And then in addition, maybe even hinting at a little bit here of day 5 from our notes at Cathedral here. So today, the properties of limits, if two functions have a limit, limit of f is L and the limit of k or of g is m, and symbolically represented there. Then if I take the limit of a sum or the limit of a difference of those two functions, limit of the product of those two functions, or the limit of the quotient of those functions, then it just turns out that the product, limit, or some difference, product, or quotient is of limit is the sum difference product of the limits of those functions. That is to say, let me just write that out then. If I would take, for instance, the limit of f of x times g of x as x approaches c, then since each of those limits exist, that would just be the product of the limits L and M. So then there's two other rules in this section. It's called a scalar multiple. If I have a scalar, just b is some constant. And I'm looking at a scenario here where the limit of b times the function ends up just being b times whatever the limit of f of x is, again, which is L. And if I raise f of x to a power, then the limit of that is L to that power. So those are just some properties in that day 4, I believe it is, that we're looking at that are going to help us do some of these limits. I want to do a little quick extra here on logic. You did these in geometry, I would think, for sure. And so P implies Q is called a conditional. It's typically an if-then statement. If P, then Q follows. I have intentionally indented the converse and the inverse. So Q implies P would be symbolically represented this way. Q implies P. And again, that would be if Q, then P. One does not imply the other necessarily. If they are both true, a conditional and its converse, you may remember that to be a biconditional. And then probably something you haven't dealt with much is the inverse, not P. I'm just negating P and negating Q. Not P implies not Q. And then the contrapositive, not Q, implies not P. If you wanted to, you could say the contrapositive is the converse of the inverse. But noteworthy here to us is the conditional and the contrapositive are always either both true or both false. They're said to be logically equivalent, just as the converse and the inverse are logical equivalents. If one's true, the other one has to be true as well. We will use this later, but I wanted to mention that to you as we look at the limit of a composite function, because the conditional is true, and I've rewritten this definition as kind of a conditional as compared to the way it was originally in the notes. If the limit of g of x as x approaches a is k, So that would be symbolically something like this. The limit of g of x as x approaches a is k. And then f is continuous. And I know we haven't talked about a definition of continuity yet, but continuous for right now is if you could draw the function, and it has to be a function still, but if you could draw the function without lifting your pencil. For right now, we'll have a little bit more next video even of what the idea or concept is of continuity. But if the function is continuous, then when x is k, then the limit of the composite function, a function built with two other functions, f of g of x as x approaches a, is going to just be f of k. So here's the end result of that. Again, the converse of this is not true. So don't overstep your bounds here. The limit of the inside function, g of x, has to exist first of all. And then the outer function has to be continuous when x is equal to that value. And if so, then the limit of the composite function is the function evaluated at k, f at k. So the question would probably come into play is, what happens if either one or maybe even both of my functions fail to exist? And that's gets the borderlines a little bit into some things I want to do in the classroom for you, for sure, when I get come back this fall. But right now, I want to look at two examples with you from day 4. They are in particular from page 11, examples 2B and 2C, just to give you kind of a little bit of an idea there of what is going on. So in 2B, they're asking for a case of the limit as x approaches 2 of f of x times g of x. And if I inspect those graphs, the limit of f of x as x approaches 2 does not exist. And the limit as g approaches 2, that does appear to be 1. So this doesn't exist, and this is 1. However, 1 times doesn't exist doesn't necessarily mean doesn't exist. So what I have to revert to then is going back to the definition of the limit. The limit only exists if the left-hand limit's equal to the right-hand limit. So I want to look at the scenario where as x approaches 2 from the left of f of x times the limit of x approaching 2 from the left of g of x. And those values, as x approaches 2 from the left, that is going to be 0. And this is going to still be, of course, 1. And that product would be 0. I'm now going to compare that as x approaches 2 from the right of f of x times the limit of g of x as x approaches 2 from the right. That still is going to be 1. F of x, however, though, is going to be 2. And, as x approaches 2 from the right, the limit of f of x is 1. And that product is therefore 1. Since the left-hand limit, 0, is not equal to the right-hand limit, then this limit does not exist. But again, it doesn't exist because f of x doesn't exist. It doesn't exist because the left-hand limit's not equal to the right-hand limit. And then in 2C, we just have another scenario that we haven't seen before. This is the limit of a composite function, f of x itself, as x approaches 0. So again, from the composite function idea, we have to know that the limit of the inside function exists as x goes to 2. So the limit of f of x, as x goes to 0, rather, is indeed going to be, as x goes to 0, the limit of f of x is going to be 2. Now, it's 2 from the left and 2 from the right. But more noteworthy, it's 2 approaching from the bottom. And we haven't seen this scenario yet, but you're going to see that this is just another technique that I'm going to use as I evaluate some of these limits. But it's approaching y equals 2, the value 2, but again, from the bottom only. The question now, is f continuous at 2? And you notice the graph of f is not continuous at 2. And therefore, we look now to a scenario where f of x, I'm going to look at the limit of f of x as x approaches 2. And again, that will be a scenario as x approaches 2 from the bottom, the negatives, and of f of x, and that value is 0. So even though it's not continuous at 2, I still can evaluate this limit. You're probably scratching your head a little bit. Well, how can you do that? Because the definition said it had to be continuous. That is, again, you're trying to apply the converse to that as compared maybe to the or to the actual conditional. We know if it's continuous and the outside limit exists, then I can evaluate it this way. But this, again, remember, is a scenario where in this case, the limit as x goes to 2 doesn't exist, but I can still evaluate the limit. So either, again, by looking at left-hand limits, right-hand limits, and there, we're also basically judging some of those of how they're approaching, even though the limit's not existing, coming up with a value of the limit as it approaches from the above or below and from there. So there's another 3 examples, I think, on page 12 that are really good for you. In example 4, involving the idea of, again, approaching from bottom or below. Make sure you look at those when you complete your notes. But we'll get into the idea of continuity next time. But hopefully this gives you a little idea of what's going on. Again, many of these problems, as you look through the notes, could be found on Mr. Records' page. And I gave you a link to that first one, I believe, in one of your notes, one of my emails. But you can look at some of those individual problems, and we'll start trying to maybe come up with those as well and enumerate those a little bit better so that you can just get right to those links. But look up those individual problems if you need to. You might have to do a little searching. They're not organized perhaps as well as you would like them to be, but you can probably find them there. And again, if you got any questions, make sure you email me, and I'll get back to you just as soon as I can. Thanks. We'll talk to you next time.